Okay, so I will continue now with the head function ft, which is represented in red as you are seeing here. So ft can be written as t plus 1 multiplied by the gate ut plus 1 minus ut. So this gives these parts, okay? And if I will add now the term minus t plus 1 times the gate ut minus ut minus 1, I will have the second part of my signal, okay? Right, so if you see now, ft is a product of time times u, and you see that it's very difficult now to evaluate the Fourier transform using the property of multiplication by time times a function, which is the step, okay, results on a differentiation in the frequency domain. So instead of using this property, we will use the differentiation property of the Fourier transform. So if you will differentiate now the function df over dt, you will have the double pulse, okay, which has the following shape. So I have minus 1 plus 1 here, minus 1 plus 1. So this is the df over dt, okay, versus time. If I will continue the differentiation, so d2f over dt2, so I will get a set of pulses at minus 1. I will have a pulse of amplitude 1. At 0, I will have a pulse amplitude 2 here. And at 1, I will have a pulse up of the same amplitude as at 1. So this is at 1. So you see that when I have differentiated twice, I got series of pulses, okay? Series of pulses. So now d2f over dt2, it is delta of t plus 1 minus 2 times delta t plus delta of t minus 1. So now when we have differentiated twice, we arrive to an expression which is only dependent on the Dirac function, and we know that the Dirac function, it's very simple to get its Fourier transform. So now if I will note f of omega to be the Fourier transform of ft, it means the second derivative of f will have a Fourier transform equal to j omega square f of omega. So the Fourier transform of this function will be equal to this, okay? So now it is sufficient to get or evaluate the Fourier transform of this function and make it equal to this one. Okay? So the Fourier transform of the second derivative of the function with respect to time is equal to exponential minus j omega, because we have delayed step, minus 2 delta gives Fourier transform equal to 2, preceded with minus, plus exponential j of omega. And this is equal by the Fourier transform property to j omega square times f of omega. So from this relation, I can get f of omega, which is in its simplified form 1 over omega 2, 2 minus 2 cos of omega, and it is also equal to 4 times sine square of omega over 2 by omega square. Now I will solve an interesting problem, which is the Fourier transform of the function ft, which is equal to minus exponential minus t squared. You see that this is very difficult to integrate exponential minus t squared multiplied by exponential of minus j of omega t from minus infinity to plus infinity. So here we will use the properties of the Fourier transform in order to get the Fourier transform of ft easily. So now you see, if I will differentiate the function df over dt, I will get minus 2t exponential minus t squared, which is minus 2 times the function. So I will preserve the f. Minus 2t times f, okay? So now I will compose the Fourier transform in both sides. It means the Fourier transform of df over dt, it will be the Fourier transform of minus 2tf. Okay? So the Fourier transform of the differential of f with respect to time, it is j of omega f of omega. So the Fourier here, it is exactly this value. And the Fourier of minus 2tf, it is exactly minus 2j df over d omega by the differentiation property of the Fourier transform. You see, by composing the Fourier transform in both sides, I got what? I got a differential equation with respect to f, capital F. So by the separation of variables, I will have df over f equal to minus omega over 2. So here I can integrate from f0 to f of omega, and here I will integrate from 0 to omega d omega. So direct calculations of this integral leads to the following. F of omega will be f of 0 exponential minus omega 2 over 4. And f of 0, it is the Fourier transform at omega equal to 0. So it is the integral minus infinity to plus infinity of exponential minus dt, which gives square root of pi. Finally, f of omega will be equal to square root of pi exponential minus omega 2 over 4, which is the final answer. And you see here how easy to get this Fourier transform by applying the properties of the Fourier transform.